Hi everyone, we are back and we are going to do our problem set 1, our first problem set solutions of this semester. I'm going to change my little pen color, even though I like the magenta actually. And we're going to answer these questions. So let's go ahead, read the following article, link here, copy and paste. Unfortunately, there's only access to basically the abstract, but that's going to be okay. Materials tetrahedron, we know in the materials tetrahedron, we have, actually, go ahead here, we have basically certain corners and points of our tetrahedron. So we know we have structure, we have performance, we have properties, and we have processes. In some way, properties, processing, or processing. Some shape or form at each corner of the tetrahedron. Again, and we want to relate essentially and look at and kind of map effectively one of the materials processes to each of these corners of the tetrahedron. So we're going to look at this this little abstract here from this article about basically block copolymers that self-assemble. And they actually self-assemble and form essentially these nanostructures. So basically, these block copolymers have a structure of one type of polymer A, another type of polymer B, and depending on essentially the size and length of these basically constituents, so basically the number of those components, the number of A block versus B block, and also an important parameter called the chi parameter, which basically allows you to kind of tune essentially the interaction, whether they like each other or whether they want to kind of stay separate from each other. You see that they can actually form a lot of these different structures. And these different structures are really, really important for things like drug delivery, and you can do lots of different things, essentially. Drug delivery, sensors, catalysis, so you can even do, basically nanophotonics. You can also, metallize and actually create little nanocircuits as well. So let's go ahead and we can kind of apply this now to our framework in terms of our materials tetrahedron. So what happens in this? So we have block A and we have block B. So we perform a process. So we either change the number of block A, we change the number of block B, or we change our chi parameter of AB. So we do some processing step where we change essentially these parameters. That will influence the structure. So we could have a lamella structure, we could have like cylindrical structures, we can have a double gyroid. So this change in process changes the structure of essentially these, nanoparticles, or basically the nanostructure of that block copolymer self-assembly. So we do this process, and you can control chi by a number of different, you could also control chi by temperature as well. And these polymers self-assemble. That's the cool aspect of it. So you do this process to change these, basically these components. It changes the structure of our material. That change in structure will change the properties. So what properties change when we change essentially the structure of that material? Well, it could be, you can change essentially, like you can think of like the time to deliver drugs. You can think about N, which is like your refractive index of your material if you're doing nanophotonics. But you're essentially changing the properties of that, with that change in structure. So by doing that change in process, we affect structure, that changes the properties, and that can change the performance of that material as well. So if you're looking at drug delivery, if you're able to tune that drug delivery release time, or that kind of sensor where, that sensor that requires essentially that specific structure, you kind of see how this process is all related. So that's it. We're just looking for kind of a quick discussion there. So don't worry too much about it. But you want to kind of relate it, and that's kind of the cool part of this class. This will become a lot easier later at the end of the semester when we've covered all these different kind of ideas of how everything connects. But anyways, intermolecular true or false statements, correct it. Intermolecular ionic bonds exhibit localized electrons. So ionic bonds do exhibit localized electrons, but it's not inter, it's intra. Intramolecular interactions like hydrogen bonds, so that's incorrect, that's inter. Have an energy greater than kT? No. Intermolecular interactions like hydrogen have an energy less than kT because they can break and reform at room temperature. Partial destructive interference leads to no signal in the intensity. No. Perfect destructive interference. That's the caveat there. To measure millimeter distances, I can use a laser. Well, no, remember on Bragg diffraction, we need to have our lambda, our wavelength of our whatever we're using to investigate structure, to be commensurate with the distance. So we know laser, depending on, usually a typical laser, you're looking at, visible light wavelength. So you're looking at hundreds of nanometers. We need something that's more on our wavelength needs to be on the order of millimeters if we want to investigate those types of distances. Covalently bonded electrons are delocalized and can break and reform room temperature. Nope. So covalently bonded electrons are localized, and covalent bonds cannot break and reform at room temperatures. They're intramolecular interactions. They have energies of about 100 kT. For Bragg interference, we need a series of perfectly arranged obstacles in a lattice. That's actually an interesting... Well, we need some arranged obstacles. It doesn't have to be perfect as well. That's kind of a caveat there. But we do need to have some obstacles. We need to have lambda on the order of d, and we need to have perfect constructive interference in order to see a signal. So there we go. Fantastic. So what type of bonding will be exhibited by Cu? Cu is a metallic bonding. Can it break and reform at room temperature? No, because the KT is greater than, or the energy of the bond is greater than KT. How are electrons distributed? They are delocalized for metallic bonds. Great, check mark. CaCl2. Now, CaCl2, we need to distinguish between if it's ionic or covalent or partially ionic covalent. We need to actually look at our periodic table. So let's go ahead. We're going to look at periodic. Where's our periodic table? Periodic. It's been a while. I'm going to just go. Periodic. Come on, where is it? Where could it be? Here's my periodic table. I don't know why that was so hard to look at it. Uh-oh. This is the fun of the live lecture. I'm going to close this. Yes, we will end the process right now. Let's go ahead and go back. Periodic table. Let's open it one more time. Because we need to look at electronegativities. So that's how we're going to distinguish between if it's ionic or covalent or in between. So let's go ahead. If we look at our handy table, we're going to see, so it's this, what is it, the second one from the bottom here? Excellent. So we need Ca, which has an electronegativity of 1, and Cl, I think, is 3.16. So let's go ahead. And remember, always use this table in this class. Those values can change. So Ca, electronegativity of 1. Cl, I believe, is 3.16, but it's always good to double check. Here we go. Let's go here. Cl, 3.16. Yep. So we will see. Oops, let's go back here. Cl is 3.16. Now remember, we have to distinguish between if it's ionic covalent, and we have, again, a pretty handy value for this class to distinguish essentially between those. So remember that we will say, and we have determined in this class, that if something is ionically bonding, let's see here, if something is ionically bonding, we're saying that the electronegativity difference, so the difference in electronegativity, needs to be greater than 1.7. 3.16, that's 2.16, so it's definitely an ionic bond. So can it break and reform at room temperature? Definitely not. How are electrons distributed? They are, if it's that strong of an ionic bond, they are very localized. I mean, but even if covalent and all those other things too. So one last, so it's saying PET. PET chemical structure. So let's see. Let's go ahead and look at PET chemical structure. PET is a polymer. It's polyethylene terephthalate. You can see that here. It's exactly your soda bottles. So we see this molecular structure here. So there's lots going on here. So you have, again, your typical kind of covalent bonded backbone. You have this big ring which induces some steric interactions because it's very large. You also have these oxygens that are going to do some kind of polar interactions. But the key idea here is, and there's going to be van der Waals interactions as usual, but you can see that PET will be composed of both inter and intramolecular interactions. So the inter ones that are less than KT will be those steric ones, those basically dipole-dipole interactions, van der Waals, et cetera, et cetera. You have your covalent interactions that are all basically, they are covalent because they're carbon-carbon backbone bonds. So these intermolecular interactions, they can spontaneously break and reform at room temperature, and the covalent ones, they cannot, and those are going to be localized interactions. There you go. CaCl2. Which is the cation, which is the anion? Ca is the cation, 2+, Cl is the anion, -1. Basically, we've kind of identified those. So remember, this will lose 2 electrons, this will gain an electron, and then there's 2 of them. CO2O3, so we know O is 2-, so 2-, 6, so we know that CO has to be 3+ here. Remember, that's how we're going to kind of typically do, with essentially those intermetallics, those metals as well. Excellent. So finally, I'm trying to model the equilibrium distance of cobalt using Lennard-Jones potential. So Lennard-Jones potential, we know that equation, and we're going to utilize that in order to solve this problem right here. So we know ULJ is equal to 4 epsilon times sigma over R12 minus sigma over R to the 6. So we're given this. We're investigating cobalt. We're told that the energy of the potential at equilibrium, so we know equilibrium is going to occur right here. So we know that this energy value is going to be -5 joules. We know that this is our equilibrium distance, so we know that right here at this distance, DULJ PR is going to be equal to 0. We know that if we're at distances from here to here, we're going to attract, because if I go from here to here, this distance to here, my energy decreases, so that means my atoms want to get closer together, so they want to attract. If I'm looking here to here, I actually want to go from here to here, meaning I want to repel. So I'm going to repel basically to the left here, and I'm going to attract, repel. I'm going to attract here. So, exactly. I'm trying to model this. So to model it, I need to find essentially what those values are in my system for Lennard-Jones potential. So let's go ahead and do that. So I have ULJ equals 4 times EPS times sig divided by R 12th minus sig divided by R to the 6. So we're given one piece of information right off the bat. And actually, we can actually look at that just a little bit. Let's see, DULJ. Actually, we can approach this from multiple perspectives. Let's start with the following. We're trying to model the equilibrium distance. We know that that equilibrium distance here and here should be equal to 2R. So if we're looking at cobalt, I want to look at and model it using cobalt's a metal. I want to look at the metallic radii, which is right below here. Cobalt is going to be cobalt 1.25 angstroms. So my equilibrium distance, REQ, is going to be equal to 1.25 times 2 times 10 to the minus 10. 1.25 angstroms times 2. So that's our equilibrium distance. So when we solve for that, we take the derivative of this function, and we're solving when does this equal to 0 in terms of R. And we see we have all these values in terms of sigma. Now, we don't want negative values, so we're going to pick this one. And basically, we want to say, well, we want this distance. We need to solve, when does this equal our equilibrium distance? And then that gives us our value of sigma. So sigma now, we know that. And we can now say, we also know at the equilibrium distance, we know the value, ULJ, of our system. So I'm going to say ULJ now, and we can see there's no more sigma unknown. So ULJ, and I want to substitute basically when we're at equilibrium. So slash dot, I'm going to change, I'm just going to say when R goes to REQ. Great. And now we know we can solve our ULJ, so we know at our equilibrium distance, we should be at minus 5 joules, because that's what our problem statement says. And now we said our epsilon is 5. There you go. That's it. I think that ends that problem. But that's how you want to kind of go about it. And again, that's a very difficult problem because it really kind of requires you to kind of manipulate and deal with these functions, but it's a fun one. So always draw it out, always write out your solutions in depth, and then we'll see you next time. Thanks.